In the late 1950s, intercontinental missiles became a central instrument of credibility in the nuclear balance. The Soviet Union had flight-tested the cryogenic R-7, capable of delivering a warhead at intercontinental ranges, but its operational utility was constrained by propellant loading times, pad infrastructure, and visible launch preparation. A weapon that could remain fueled for extended periods, with a smaller logistical footprint and quicker readiness, was an explicit requirement set before the design bureaus. The Ministry of Defense and the Military Industrial Commission directed multiple organizations to pursue storable propellant missiles using nitrogen tetroxide and unsymmetrical dimethylhydrazine, accepting known toxicity and corrosiveness in exchange for readiness and storage advantages. This policy preference established the technical path that produced the two-stage R-16 under OKB 586 in Dnipropetrovsk, with Mikhail Yangel as chief designer. Internal political pressures sharpened that requirement. After the May 1960 U-2 incident and the breakdown of the Paris summit, Nikita Khrushchev emphasized demonstrations of strategic capability that could be shown to foreign audiences and to Soviet party organs alike. Within the Presidium and the State Committee for Defense Technology, deadlines were calibrated to anniversaries and conferences, including the approaching 7th November celebrations. Senior marshals and industry managers were accustomed, since wartime, to translate political directives into accelerated schedules. Marshal Mitrofan Nedelin, First Deputy Minister of Defense and Chief Marshal of Artillery, was appointed chair of the State Commission for R-16 flight tests at the Baikonur test range. His presence at the pad would carry weight across the military-industrial complex, signaling that the program's timeline was not discretionary. The test range itself reflected both capability and constraint. Baikonur possessed rail access, propellant production, and specialized service towers, but it also inherited procedural traditions formed around the 7 and earlier ballistic missiles, where extensive on-pad work was routine. Range regulations mandated safety perimeters during fueling, evacuation thresholds for toxic vapor detection, and hierarchical authorization for maintenance under pressure. However, in practice, these rules coexisted with a culture of improvisation. The integration of launch crews from the strategic rocket forces, designers from OKB 586, range specialists, and commissioned officers created overlapping lines of responsibility. In this environment, responsible executor status, a formal designation carried by a department chief or brigade commander, could blur when a senior official remained physically present and issued verbal instructions. The technical features of the R-16 created specific risks. Its first stage used 2 A-series engines fed by hypergolic propellants with pneumatic and electrical interlocks to prevent premature ignition. The second stage sat above, separated by an interstage lattice, with its own autonomous control system and batteries. During assembly and rollout, protective devices and plug-in test circuits simulated launch commands while isolating live firing circuits. The system architecture assumed that, prior to fueling, live pyro devices would remain safed, and that any transition to a combat configuration would proceed through documented steps. The October schedule compressed these steps. Substitutions were authorized for components that showed test stand anomalies, and a logic change in the second stage control circuit was introduced close to rollout, requiring revised procedures. These decisions were made by engineers and military testers within the State Commission's framework, and were recorded through technical orders, but the accumulation of small deviations increased dependency on human coordination at the pad. The senior officer's presence near hardware had a precedent. In the Great Patriotic War, commanders often remained forward to verify sappers' work, artillery preparation, and bridge crossings. The legitimizing logic was personal responsibility. A commander who witnessed an operation could attest to its readiness and, if necessary, accept fault. In peacetime test activity, This translated into senior officials positioning themselves at the most critical location, the pad, especially when political calendars were tight. The intention was not to discard safety regulations, but to supervise their execution, to remove bureaucratic delay, and to authorize on-the-spot remedies when instrumentation or valves did not behave as expected. The outcome, however, was that authority, risk, and physical proximity converged. Within OKB 586, Yangel and his deputies sought to reconcile schedule pressure with engineering caution. Factory testing at Dnipropetrovsk had identified issues in propellant feed dynamics and command sequencing that were not fully reproducible at the range due to differences in ground support equipment. The Range Service Organization, for its part, managed storage, mixing, and transfer of oxidizer and fuel under meteorological constraints, while the Strategic Rocket Forces Brigade, responsible for the launch, carried its own training standards and readiness metrics. Each group used its own documentation set and vocabulary, though all fell under the State Commission's protocols. This multiplicity complicated real-time interpretation of alarms, particularly when condition indicators could reflect sensor faults, transient pressure pulses, or genuine hazards. Soviet secrecy norms shaped communication before and after the tests. The Baikonur range operated under cover designations. Incident reports were classified and circulated to a restricted set of ministries and party secretaries. Journalists and provincial party members had no access. These norms had been established in wartime and codified in the early Cold War through penalties for disclosure of defense secrets. Practical consequences followed. Risk communication to the workforce emphasized discipline and obedience. Range workers were briefed to treat all anomalies as internal matters, and external medical support plans assumed containment within the garrison. Thus, even the planning for emergency response was embedded in an assumption of self-sufficiency and silence. Weather and daylight in late October in the Sier Daria steppe narrowed operational windows. Temperatures favored stable propellant temperatures, but wind gusts complicated tower operations and venting. The schedule still prioritized an autumn attempt, with the expectation that a first flight before November would demonstrate that a storable propellant ICBM had moved from concept to reality. The United States had fielded early Atlas variants and was progressing on Titan I while preparing Polaris for sea deployment. Soviet intelligence assessed that American missiles were entering dispersed basing and that warning times were shortening. Within this framework, the R-16 promised a force that could occupy more sites, remain loaded for longer durations, and yet be serviced with fewer conspicuous preparations. Strategic rationale, in other words, translated directly into tolerance for on-pad corrective work. Eyewitness accounts and later commission materials highlight a final contextual point. Authority gradients were steep. Junior engineers reported to shop chiefs, who reported to deputy chief designers. Range officers reported through brigade and division chains. But when a marshal remained at the pad, even formal stop-work rules were difficult to enforce. Technicians described reluctance to evacuate when senior leadership stayed in place. Conversely, senior leadership remained in place to signal commitment and to expedite decisions. This mutual reinforcement of presence, leaders staying to encourage effort, workers staying because leaders stayed, was not a codified procedure, yet it arose predictably from shared assumptions formed in wartime and sustained by post-war institutional practice. By the morning of October 24, 1960, these preconditions had aligned: a strategic requirement for a ready storable propellant ICBM, a compressed political timeline, a design still undergoing last-minute procedural changes, a range culture where on-pad intervention was normal, secrecy that constrained external scrutiny, and a leadership ethos that equated proximity with responsibility. The pad at Baikonur bore the physical signatures of those choices. Service towers crowded with mixed teams. hazardous fluids already transferred, interim test circuits connected, and senior officials positioned to observe and decide. The catastrophe that would follow did not originate in a single gesture, but in this layered context of technology, organization, and doctrine carried from war into peace. At dawn on the 24th of October 1960, the launch complex was brought to an operational posture under the State Commission chaired by Marshal Mitrofan Nedelin. The Duty Meteorological Group reported acceptable conditions for loading. Range operations authorized the transfer of nitrogen tetroxide and unsymmetrical dimethylhydrazine to the two stages of the R-16. The first operations block involved inerting lines, verifying valve actuation, and pressurizing helium bottles. Mixed crews from the Strategic Rocket Forces Brigade, OKB 586 engineering teams, and Range Technical Services moved by checklists translated from factory documentation, while the command post collated subsystem status lamps and interlock positions. The program's chief designer, Mikhail Yangel, was present with his deputies. The range commander coordinated pad perimeter control. Medical and fire units were placed in pre-designated zones. By mid-morning, the fueling sequence encountered warnings related to the second stage control circuit. Test plugs indicated inconsistent continuity in a channel responsible for arming ignition commands. A logic revision introduced shortly before rollout required precise sequencing of power supplies and test connectors. The anomaly suggested either a sensor fault or cross-coupling through harness connectors. The On-Site Engineering Council, a routine assembly of subsystem leads, convened near the service tower. Options considered included rolling back to a defueled state for bench diagnostics or conducting on-pad corrections under strict lockout. The State Commission elected to proceed with on-pad checks to preserve the day's readiness, with the proviso that explosive devices remained safe until the fault was isolated. Written authorizations were issued for specific panels and junction boxes to be accessed. Throughout late morning and into early afternoon, technicians worked inside the service tower and on elevated platforms. The first stage remained under pressure. The second stage batteries were being conditioned. Witness statements later recorded that protective devices and safing pins were pulled and reinstalled multiple times to permit continuity measurements and simulated command injection. Range safety rules called for evacuation to a defined distance during any change in system state. In practice, the area around the vehicle remained populated by several dozen specialists whose tasks were serialized but spatially overlapping. Nedelin established himself at a table near the base of the tower to receive direct reports, while the State Commission Secretariat recorded deviations from the nominal timeline. An intermediate system test early in the afternoon produced an off-nominal indication in the second stage ignition path. Electrical leads were rerouted to bypass a suspected faulty connector. This required partial removal of protective covers. The updated wiring was to be restored to flight configuration before any arming procedure, but the presence of live power sources meant that inadvertent signals could not be excluded. A request to depower the second stage network conflicted with the planned continuity tests that required energized circuits. The technical leads agreed to proceed with a constrained energization, accompanied by a standing order that no arming commands be issued and that pyrotechnic chains remain interrupted. As daylight began to wane, the command post weighed the remaining steps needed to certify the vehicle for a first flight attempt. The first stage propellant temperatures were within limits. The pressurization regime had held. Telemetry vans had acquired stable channels. The unresolved item was the reliability of the second stage ignition logic under flight-like power sequencing. A final attempt was authorized to reproduce the nominal path while observing for spurious signals. Personnel were allocated to discrete jobs. One team monitored bus voltages, another observed relays, a third checked isolation between the second stage ignition circuit and any unintended return paths. The number of individuals present within the immediate pad area remained higher than safety manuals anticipated for a fueled vehicle. At approximately the time set for the last continuity test, a series of events occurred in close succession. Power was applied to the second stage control unit, and a transient in the circuit produced an ignition command despite the absence of a formal arming sequence. The second stage engines ignited on the pad. The exhaust impinged on the first stage structure, rapidly compromising tanks containing hypergolic propellants. Structural failure propagated through the interstage lattice. Hypergolic mixing produced intense combustion at ground level. The resulting fire and pressure effects swept the area under and around the service tower. Immediate reactions followed the established lines of responsibility, but were constrained by the environment. Operators in the command post initiated a range emergency signal and attempted to cut power to pad systems. Fire units, pre-positioned at safe standoff distances, advanced but faced expanding pools of burning propellant and dense toxic fumes. Personnel on the platforms and at the base of the tower had minimal shelter. Many were overcome by heat and combustion products within seconds. Those at the periphery moved away along service roads. Some attempted to assist others, but were forced back by secondary flashes as tanks and lines ruptured. The State Commission fractured into its functional components as individuals sought to re-establish command. Surviving officers initiated headcounts by brigade and shop numbers. Medical teams set up triage at points downwind where air remained breathable, treating burns and inhalation injuries. Communications with higher headquarters reported a pad incident during test operations and requested additional medical transport from the garrison. The decision was made to confine public communications within classified channels, consistent with standing instructions governing test range accidents. Chain of command considerations carried through the first hour after the event. With senior leadership casualties, deputies assumed roles to secure the site, prevent unauthorized entry, and preserve documentation. Engineering leads gathered any surviving test logs, checklists, and instrument records. The pad remained hazardous due to residual propellant and damaged structures. Fire units continued suppression using previously planned agent quantities for oxidizer and fuel spills, adapting to volumes that exceeded typical contingency models. Eyewitness accounts agree on several factual elements. Ignition of the upper stage on the pad, rapid structural failure of the lower stage, an intense ground-level fireball, and heavy casualties in the immediate vicinity. The differences among testimonies concern exact timing of preceding actions, the status of specific safety interlocks, and which authorizations were active in the minutes before ignition. These discrepancies reflect the complexity of simultaneous tasks and the limited field of view available to any one participant. Subsequent commissions would attempt to reconcile them by correlating personal recollections with physical evidence and surviving instrument traces. By late evening, the range commander ordered a full halt to further operations and established a restricted zone around the complex. Bodies were recovered as conditions permitted. Lists were compiled by unit and organization. Surviving members of the State Commission prepared preliminary incident descriptions for transmission to ministerial superiors. The opening phase thus closed with the immediate sequence documented: an on-pad corrective effort under fuel load, an unintended ignition of the second stage, catastrophic failure of the vehicle at the pad, and an emergency response conducted within the constraints of toxic combustion and classified procedures. The strategic intent behind the October 1960 campaign was explicit and quantifiable. For the Ministry of Defense and the Military Industrial Commission, an operationally practical intercontinental missile had to transition from design validation to a repeatable launch cycle that could be taught to brigades and reproduced at dispersed sites. The R-7 had served as a proof of concept. The R-16 was planned as a force element. Targets set by party and government organs translated into milestones: assembly integration at the factory, acceptance at the range, fueling trials, a first flight to verify stage separation and guidance, and a second flight to confirm reliability. A successful first launch before early November would allow the State Commission to report that a storable fuel system had crossed from experimental status into qualification, unlocking resources for serial production and deployment tables for strategic rocket forces formations. Each stakeholder translated this objective into planning tasks. OKB 586 under Mikhail Yangel produced the launch preparation sequence, including wiring diagrams, interlock logic, and test plug configurations for both stages. The Strategic Rocket Forces Brigade attached to the range developed a manning plan by specialty: fueling, pneumatics, pyrotechnics, guidance, telemetry, aligned by shift to maintain continuity across fueling windows. The Range Service Organization prepared propellant storage, transfer lines, neutralization agents, and meteorological support. The State Commission coordinated these plans into a single timeline with decision gates that required signatures from subsystem leads and the chief designer. The presence of Marshal Mitrofan Nedelin as chair reduced latency between finding a fault and authorizing a corrective measure on the pad. The logistics plan addressed distance, hazard, and redundancy. Rail consignments brought airframes, engines, and electronics from Dnipropetrovsk to Tyuratam. Acceptance teams checked serial numbers and documented substitutions. Hypergolic propellants were stored in segregated tanks, with dedicated pumps and color-coded lines to prevent cross-connection. Firefighting units received agent quantities, size for spill scenarios, derived from earlier missiles, but scaled upward for the two-stage R-16 volumes. Medical units staged decontamination supplies and transport vehicles at pre-assigned posts. Communications vans linked the pad, command post, telemetry stations, and the range dispatcher through wired and radio nets, with a documented fallback if one channel failed. These measures were intended to convert hazardous steps into routine practice through procedure, not improvisation. Technical doctrine balanced two imperatives: keep explosive chains interrupted until a final arming order, and verify as much of the system as possible under flight-like conditions before the countdown. The verification imperative drove use of energized circuits, simulated commands, and temporary removal of safing pins to measure continuity through real harnesses. The interruption imperative required dummy loads, removable jumpers, and physical gaps in pyro lines until late in the flow. The planning documents attempted to sequence these principles so they did not conflict. However, compressed calendars created pressure to overlap tasks. A continuity test that, in isolation, required a live bus might be scheduled while fueling crews were still present on the tower. The risk calculus assumed disciplined adherence to stop-work rules whenever a configuration boundary was crossed. Comparative intelligence awareness informed senior guidance. Soviet assessments of United States programs noted that Atlas variants required extensive pad support and used cryogenic oxidizer, while Titan I promised improved basing, and Minuteman, in planning, sought solid fuel and silo launch. Polaris offered survivability at sea. Against this landscape, the R-16's storable propellants, planned road mobility of later derivatives, and reduced pre-launch visibility were seen as compensatory advantages. Strategic planners translated these assessments into directives to minimize pad time and to structure checklists that could be executed by brigades under field conditions, not only at Baikonur. The first flight at the range thus had an explicit downstream purpose: to certify procedures that would later be distributed as regiment-level doctrine. Personnel planning reflected wartime sharpened norms. Redundancy in critical tasks ensured that if one specialist was unavailable, another could proceed. Officers were authorized to resolve discrepancies at the point of action, within the bounds of written orders. The decision matrix embedded authority at multiple levels, but it also assumed that higher authority physically present at the pad would arbitrate swiftly. Documentation routes were short. A deviation report moved from a shop chief to the chief designer's deputy, then to the State Commission table within minutes. Time saved in transmission was expected to translate into calendar gains. The planning philosophy regarded time as a controllable variable if responsibility was concentrated near the hardware. Safety planning, on paper, was detailed. Perimeter distances were specified for various states: unfueled maintenance, fueling under pressure, and armed configuration. Gas detection thresholds triggered evacuation. Protective clothing standards were listed for crews working near oxidizer and fuel. Lockout-tagout protocols for electrical work were defined, with special provisions for systems using shared grounds or common return paths. The Commission's schedule incorporated evacuation periods while configurations changed. Yet the same schedule also embedded inspection checkpoints, where senior observers would walk the pad to verify that procedures were being followed. The expectation was that oversight and safety could coexist spatially, provided that explosive chains were open and that power buses were controlled according to sequence. The propaganda dimension was a planning variable rather than an afterthought. A timely demonstration of a new class of missile would be reported not in open press, but within the party and military leadership, reinforcing narratives of technological momentum. Range secrecy rules and cover names were part of this system. If the flight succeeded, a controlled cascade of briefings would attribute progress to the political leadership, the Ministry of Defense, design bureaus, and the strategic rocket forces. If it failed without casualties, the same apparatus would absorb the event as a test anomaly and adjust schedules. Catastrophic scenarios were addressed in classified contingency plans that prioritize site control, document preservation, and internal reporting over external messaging. Miscalculations emerged where doctrines intersected. The test program required final confirmation that the second stage ignition logic survived realistic power sequencing. Implementing that confirmation on a fully fueled vehicle placed instrumented verification and hazard containment in direct proximity. The assumption that interruptions in pyro chains and the presence of safing devices would be sufficient to prevent energy flow into ignition paths proved optimistic when late logic changes demanded energized checks. The decision to perform on-pad modifications rather than roll back for bench work traded one risk, calendar slip, for another, complexity under fuel load. The planning documents did not ignore these risks. They accepted them under the belief that tight supervision could compensate. Resource allocation tied planning to execution tempo. Spare components for suspect connectors and relays were staged at the pad to avoid delays. Engineers capable of reworking harnesses were assigned to the same shift as fueling crews, so a corrective action could be initiated without waiting for a changeover. Telemetry specialists configured channels to capture detailed traces during ground tests, to support post-test analysis even if a flight did not occur. Fire units rehearsed approach routes with vehicles loaded to wait, to ensure that acceleration and braking matched real conditions. Each of these measures aimed to remove friction from the sequence, but each also increased the number of people and vehicles committed to the immediate pad environment. Command communication rehearsals completed the planning picture. The Commission conducted tabletop drills on the morning of operations to step through who would authorize power application, who would control removal and reinsertion of safing pins, and how anomalies would be called and recorded. These drills assumed clear lines. If a red lamp illuminated, work halted. The area was cleared according to the safety map, and the anomaly was discussed at the Commission table before any further action. The presence of senior leadership created an alternative path. Direct verbal instructions could be issued to continue a measurement or to reattempt a step while observers remained on site. The plan's strength, short decision loops, thus contained its own vulnerability when those loops bypassed the pauses built into the safety flow. Strategic goals and planning before the first R-16 launch at Baikonur therefore combined technical doctrine, political calendar, and a command ethos that rewarded decisive proximity. Every document in the flow aimed to reconcile verification thoroughness with hazard control, speed with caution, publicity with secrecy. The configuration that stood on the pad on October 24, 1960, embodied those reconciliations. A vehicle designed for rapid readiness, a crew trained to compress operations, a leadership structure built to decide at the point of risk, and a schedule calibrated to national milestones. The subsequent events would test whether that balance could hold when logic revisions, live propellants, and concentrated authority met on the same platforms under a diminishing autumn light. The immediate consequences of the pad event unfolded as a sequence of discrete actions that mirrored the structure of the test operation itself, but now under emergency rules. Range dispatchers transmitted the pre-arranged alarm code over wired and radio nets. Loudspeakers at the service area instructed non-essential personnel to withdraw to designated assembly points. The fire service, equipped with vehicles configured for oxidizer and fuel spills, advanced along the rehearsed approach roads, while a second echelon remained at the perimeter to stage additional agent tanks. Medical detachments established triage downwind based on wind flags and meteorological updates, separating treatment areas for thermal injury from those for inhalation exposure. Security companies established cordons at prescribed radii to block unauthorized movement toward the pad and to prevent contaminated equipment from leaving the zone without decontamination. Operating inside the response plan's geometry, the fire commanders executed a containment strategy rather than an immediate close assault. Pools of mixed hypergolic propellants continued to burn while damaged lines vented residues. Water use was controlled to avoid spreading contamination. Foam and neutralizing agents were applied in arcs to isolate sources. The service tower's integrity degraded as heat affected structural members. Collapse risk forced repeated repositioning of vehicles and crews. These movements consumed minutes, but they preserved the ability to sustain operations over the first hour. Concurrently, a telemetry van that had retained power recorded signal traces until heat and smoke forced shutdown. Those traces would later assist investigators in reconstructing the timing of the unintended command path. Within the inner zone, survivors self-organized by the affiliations they knew best. Technicians from OKB 586 sought their shop chiefs and deputies. Strategic Rocket Forces specialists concentrated by specialty: pneumatics, fueling, electrical. Officers from the State Commission Secretariat began collecting names against morning roll lists. Short lists of missing personnel were compiled and relayed outward to inform medical staging of probable patient loads. The command post, now an emergency coordination node, assigned liaison officers to fire and medical leaders to keep the State Commission informed without generating conflicting orders. This arrangement, although improvised, reflected the pre-existing division of labour at the range. The Commission decided, the range commander executed, and service chiefs ran their specialties. Early rescues occurred in pockets of survivability created by terrain, equipment shadows, and the chance positioning of individuals. A small number of personnel on the outer platforms descended along the side opposite the blast and reached the access road. Others inside cable trenches had partial shelter from radiant heat and emerged after oxygen levels stabilized. Eyewitness recollections recorded that some individuals escaped because a leader ordered a brief halt minutes before the ignition. Others survived because they had been dispatched to fetch tools or documents. The chief designer, Mikhail Yangel, was absent from the immediate pad area at the critical moment and therefore remained able to participate subsequent coordination and initial statements of technical conditions known before the event. Such details, while personal, entered the factual record because they helped investigators map who was in position to witness which steps. Documentation control became a first-order priority once flames subsided at the periphery. The Commission directed the recovery of test logs, checklist copies, and instrument paper rolls from vans that could be approached safely. Officers sealed recovered materials in marked envelopes and registered each item against a receiving list. The objective was to preserve a chain of custody for later reconstruction without delaying rescue actions. Where vehicles were lost, the responsible specialists were asked to record from memory the steps they had performed, including the positions of switches, the presence or absence of jumpers, and the timing of verbal authorizations. These notes, taken within hours, would later serve as a baseline for the commission of inquiry when memory discrepancies emerged. The range's medical system absorbed casualties according to pre-planned dispersion. The first echelon treated and stabilized. The second echelon transported to the garrison hospital, where surgical teams had been quietly mobilized as part of the standard range alert. Protocols for toxic exposure emphasized removal of contaminated clothing, irrigation of exposed skin, and oxygen support. Surge capacity was created by reassigning wards and by requisitioning transport vehicles from nearby units. Because public disclosure was not authorized, traffic control and patient movement were managed under routine military dispatch codes, rather than visible emergency convoys. Families and civilian workers within the closed city were not informed in open channels. Notifications were handled through unit commissars and plant liaison officers. Parallel to life-saving work, site control escalated. The range commander suspended all operations beyond the affected complex and instituted a site access regime based on written passes countersigned by security. Engineering reconnaissance teams entered the pad area in protective gear to map residual hazards, tank fragments, pooled oxidizer, damaged electrical cabinets, and unexploded pyro devices. They placed flags and markers to guide later evidence collection and to signal zones that remained dangerous to approach. This mapping allowed the fire service to re-engage selectively and enabled recovery teams to begin systematic searches when temperatures dropped below thresholds specified for safe entry. Communications upward followed a form established for classified incidents. A preliminary signal, incident, casualties, cause under investigation, went to the Ministry of Defense and the State Committee for Defense Technology. A second, more detailed narrative summarized the sequence known so far and listed the senior officials present and their status. Requests followed for additional decontamination units, medical specialists with burn experience, and investigators from design bureaus not directly responsible for the R-16 to provide an external technical perspective without conflicts of interest. The decision to involve outside bureaus did not imply assignment of fault. Rather, it broadened the base of expertise available for immediate technical interpretation. The first hours generated competing imperatives: move quickly to rescue and stabilize, and move carefully to preserve evidence and prevent secondary harm. Range leadership addressed this by temporal separation. Rescue and fire suppression dominated until on-site commanders declared thermal hazards reduced. Only then did structured evidence recovery begin. Even then, any finding that suggested an ongoing hazard, pressurized bottles, smoldering insulation, or damaged batteries, triggered a rollback to suppression and isolation. This oscillation between modes continued through the night, pacing the work according to evolving conditions rather than fixed deadlines. Morale and discipline were affected in predictable ways. Witnesses noted that some junior personnel, after assisting peers, sought direct orders from the highest-ranking officer present, a behavior traceable to the authority gradient typical of the test program. Others adhered strictly to unit leaders and avoided ad hoc directives. Neither approach was inherently unsafe, but the coexistence required deliberate deconfliction by the range commander, who reiterated that all orders would run through the service chiefs to avoid contradictory actions. The presence of surviving senior figures at the coordination point provided a focal node for decision flow. Information management within the closed city began immediately. Press organs did not report the event. Public spaces continued normal schedules. Inside units and shops, however, attendance rolls reflected absences. Commissars and political officers addressed workers with neutral statements. An incident had occurred. Operations were paused. Assistance teams were at work. Further information would come through official channels. The purpose was to stabilize the workforce, prevent rumors that might compromise secrecy, and maintain the capacity to support recovery and investigation in the following days. By the end of the first night, the pad area was divided into mapped sectors with documented hazards. Fire sources had been reduced to isolated hotspots. Triage had been completed for those reachable, and evidence preservation had begun. The range commander issued an order freezing any alteration of recovered wiring, connectors, and control units without documentation and witnesses from multiple organizations. The Commission prepared its first formal preliminary report for transmission to Moscow, noting that the configuration included a fueled first stage and energized second stage systems, that an ignition of the upper stage had occurred on the pad, and that casualty numbers were significant, with identification in progress. The initial engagement phase thus closed with a stabilized site, a functioning but constrained command structure, and a baseline documentary record from which the investigative and political dimensions would expand in the ensuing days. Escalation began as soon as the site was secured enough to permit sustained work. The range commander halted all non-essential activity across adjacent complexes, diverting personnel and equipment to the affected pad. This concentration created secondary constraints. Propellant transfer elsewhere was postponed. Communications channels reserved for routine telemetry now carried emergency coordination. Transport assets that normally cycled supplies across the steppe were reassigned to medical and fire movements. Triage points expanded into temporary wards. The garrison hospital activated reserve operating rooms and requisitioned blood products from nearby military units. Medical officers recorded exposure categories, thermal injury, inhalation, mixed trauma, to prioritize scarce ventilators and dressings. The number of fatalities already exceeded the capacity of on-site mortuary facilities, forcing the establishment of a controlled temporary holding area under guard pending identification. Command challenges multiplied as the human and technical tasks overlapped. The State Commission required uninterrupted access to surviving documentation and hardware. Rescue teams needed space to operate safely. Fire units demanded corridors for foam and neutralizing agents. To manage friction, the range commander shifted to a sector model. Each mapped zone had a single lead, with written passes allowing entry to those with specified tasks. This structure reduced cross-traffic but slowed work where two functions met, such as near the base of the service tower where evidence recovery and suppression continued in alternating cycles. The Commission approved the creation of a central log that recorded every removal, relocation, or adjustment of hardware with serial numbers and timestamps to prevent later disputes over provenance. Secrecy protocols intensified. Communications upward used pre-formatted incident messages, and the closed city's internal networks circulated only administrative directives. Unit commissars prepared families for delayed returns without describing causes. Personnel lists took on a dual role: humanitarian notification and program continuity planning. Every absent specialist implied a gap in the skill matrix for the R16 and related programs. Plant liaison officers at OKB 586 began compiling rosters to replace critical functions. Wiring specialists, pneumatics technicians, test engineers, recognizing that training pipelines, not only hardware, would determine recovery speed. The Strategic Rocket Forces Directorate noted that brigade-level readiness for storable propellant systems would have to be recalculated as test-derived procedures had lost senior practitioners. Politically, the event entered a phase where classification and responsibility intersected. A government-level commission was assembled from the Ministry of Defence, the State Committee for Defence Technology, the Procuracy, and security organs. Its initial mandate combined fact-finding, what sequence occurred, with immediate risk control, what measures were required to prevent recurrence at other pads or plants. This produced rapid interim orders, pause on pad logic modifications under fuel load, review of safing pin procedures across storable propellant programs, inventory of live test plugs, and their lockout practices. These were not final judgments, but crisis directives designed to reduce the chance of a second accident while the technical reconstruction proceeded. Internationally, the crisis generated little overt response at first. The site's remoteness and the absence of open press coverage meant foreign observers had only indirect indicators: irregular rail movements, changes in coded radio traffic, or later satellite imagery of damaged infrastructure once reconnaissance coverage permitted. Domestically, however, the leadership confronted calendar implications. November demonstrations traditionally included references to industrial and military progress. Planners removed prospective language about near-term missile achievements from internal speeches and rephrased briefings to emphasize reliability and methodical development. The decision preserved secrecy while adjusting expectations inside the defense industrial network. Terrain and weather imposed their own escalation dynamics. Evening temperatures reduced some vapor hazards, but increased challenges for prolonged outdoor work. Decontamination teams established heated tents for changing and washing to prevent hypothermia. Foam residues and oxidizer neutralization products required controlled collection. Environmental officers documented soil removal volumes and designated lined pits for temporary storage, anticipating later remediation decisions. None of these tasks advanced the launch program directly, yet each was necessary to reopen the pad without introducing long-term hazards to personnel or equipment. The personnel crisis deepened as identification advanced. Senior positions, shop chiefs, deputy designers, battery chiefs, appeared on casualty lists disproportionately because leadership presence near the pad had been high at the critical moment. This skew affected decision networks. To maintain continuity, the Commission authorized acting appointments from adjacent programs, accepting short-term inefficiencies from unfamiliarity over paralysis from vacancies. Range authorities scheduled structured debriefs for all survivors by functional group, both to capture technical information before memory degraded and to stabilize teams by returning them to procedurally familiar environments. Conflicting imperatives about movement crystallized in debates over partial reopening of unrelated pad operations. On one hand, continued activity elsewhere preserved schedule credibility and signalized control. On the other, shared services, fire units, medical capacity, communications remained constrained. The compromise was a tiered restart. Low-risk tasks under unfueled conditions resumed with enhanced oversight, while any activity involving hazardous fluids or explosives awaited the Commission's interim technical orders. This approach accepted near-term slippage to concentrate scarce safety resources on the high-risk recovery zone. Information control generated its own operational burdens. Maintaining silence required deliberate coordination among units, plants, and ministries, increasing the volume of classified correspondence and the number of controlled documents in circulation. Each added opportunity for procedural error, misaddressed packets, incomplete distribution lists, carried security risk. Security officers instituted spot checks and required countersignatures on courier logs to ensure traceability. The result was slower administrative throughput even for routine requisitions, a friction that leadership accepted to protect classification. The crisis also triggered comparative reviews. Analysts assembled data from earlier range incidents involving other missile families to identify commonalities in arming logic, ground support equipment interlocks, and crew proximities during energized tests. Where earlier anomalies had produced near misses rather than casualties, those records now assumed new relevance. The Commission ordered cross-program briefings so that engineers on liquid oxygen systems, solid fuel stand tests, and cruise missile programs could identify whether their procedures contained analogous failure modes. The intent was not to generalize prematurely, but to use the window of heightened attention to correct systemic vulnerabilities. By the close of the first 48 hours, escalation had transformed into a structured crisis management regime. The pad was segmented, hazards mapped, casualties documented, and an investigative framework installed. Range operations adopted a constrained restart elsewhere under amplified safety oversight. Politically, the leadership signaled internally that schedule priorities would be recalibrated in favor of reliability measures pending technical conclusions. The event had expanded from a single pad accident to a system-level challenge. Personnel pipelines, documentation practices, interlock doctrines, and communication structures across the missile enterprise now fell within the scope of the emerging inquiry. The peak phase coalesced around two parallel operations: a full technical reconstruction under government mandate and a coordinated reconstitution of the missile workforce. The Commission divided tasks into discrete lines of effort with measurable outputs. One group mapped the electrical logic of the second stage ignition and command paths, physically tracing every conductor from the control unit to the pyro initiators and documenting shielding, connectors, and grounds. A second group analyzed pneumatic and hydraulic records to confirm pressure histories in the first stage tanks and lines. A third compiled human timelines by aligning watch times, pad loudspeaker announcements, and checklist signatures. Each team produced interim tables, device serials, measured resistances, relay dwell times, bus voltage excursions, to permit cross-correlation. This approach treated the accident as a system outcome rather than a single fault, which allowed findings to be tested against instrument traces preserved in the telemetry van and against survivable fragments of the vehicle. Hardware recovery proceeded with the discipline of a field operation. The pad was gridded, and every fragment above a threshold size was numbered, photographed, and bagged with location coordinates. Investigators prioritized components capable of preserving electrical state at failure: relay housings, switch wafers, battery terminals, on the assumption that residual soot patterns and metal deformation could indicate whether a circuit had been energized. The control unit shell from the second stage, recovered in distorted form, was opened under witness to inventory board positions and jumper configurations. Findings were compared to the last approved wiring diagram to identify any differences introduced by late logic changes. When discrepancies surfaced, the Commission did not assume error. It sought the corresponding authorization documents to distinguish sanctioned modifications from improvised workarounds. Reconstruction extended beyond the pad. In Dnipropetrovsk, OKB 586 created test stands that reproduced the disputed segments of the command chain with production parts from the same lots as those on the damaged vehicle. Engineers replicated the power-up sequence reported by survivors, battery connection order, bus energization timing, test plug insertion, and measured whether transients could propagate to ignition lines if safing pins were absent, or if isolation was incomplete. Results were documented in tables that linked precise timing offsets to relay response, aiming to demonstrate whether an unintended ignition command was possible under the reported configuration. Plant metrology sections calibrated instruments against reference standards to preempt later challenges to measurement credibility. Casualty accounting reached its maximum intensity in this period. Unit clerks and factory liaison officers assembled consolidated roles that listed each name with organizational affiliation, duty at the pad, and identification status. The working range of fatalities recorded by on-site lists and hospital reports exceeded the capacity of initial estimates, forcing a revision of support plans for families and a recalculation of available specialists by discipline. The Commission treated the numbers as operational data. Each confirmed loss meant a gap in a checklist that future launches would require. Plans for accelerated retraining were drawn up, with course syllabi, instructor assignments, and target dates. In parallel, administrative orders formalized benefits and transfers for dependents according to closed city regulations, executed without public ceremony but registered in personnel files. At the political apex, directives reached across programs. An immediate order suspended on-pad logic alterations under fuel load and required that any verification involving energized circuits be conducted with physical interruptions in pyro paths, verified by 2 independent sign-offs. A second directive mandated that safing pin control pass through a documented custody chain with timestamps for removal and reinsertion, and that any concurrent task in the vicinity cease during such transitions. These were not novel concepts. They codified practices that had existed unevenly. The Commission's peak phase work was to standardize them with unambiguous definitions, to remove room for verbal exceptions, and to align terminology across design bureaus and military test units. The cultural dimension reached its most explicit articulation here. The Commission's transcripts show repeated attention to the wartime-derived habit of command presence at the point of risk. Rather than appraise motives, the inquiry measured consequences. When senior leaders positioned themselves at the pad, evacuation thresholds were not invoked by subordinates. When leaders departed to confer, technicians felt freer to suspend work during ambiguous indications. The policy response did not rely on exhortation. It created protocol triggers that did not depend on rank. Gas detection over a threshold or movement of specific switches would lock access automatically, and it introduced negative authority signs. A designated safety officer could halt work visible to all networks, with a formal path for appeal, but without the need to seek permission to stop. The peak also produced the most far-reaching technical prescripts for storable propellant systems. Interlock design reviews were ordered for all vehicles using nitrogen tetroxide and UDMH. Ground support equipment received requirements for galvanic isolation, dedicated returns, and standardized connector keys to prevent mismating. Acceptance tests added steps that verified the absence of latent conductive paths under induced transients. Documentation sets were restructured so that temporary jumpers and test plugs had unique identifiers and life histories, preventing the quiet reutilization of improvised devices beyond their intended context. The Commission's aim was to remove hidden couplings that could convert a diagnostic into an inadvertent command. Operationally, the range rehearsed a new pattern for the heaviest risk steps. Evacuation radii for fueling and energized testing were expanded, and timing windows were refactored to avoid overlap. A controlled trial introduced a staggered clear and cool protocol. Before any power application to control units, the pad was cleared to a specified distance. A radio net carried a standardized phrase. A second officer, looking only at perimeter cameras and gas readings, had to confirm the clearance before the sequence could proceed. The rehearsal treated time as a resource, no longer shaved by co-locating tasks. Reports recorded the cost, more hours per attempt. They also recorded the benefit, fewer personnel within hazard zones during energized states. International context remained largely inferential, but at the apex of internal decision-making, the strategic program was reframed in concrete terms. Schedules were revised to incorporate new test categories, off-pad hot fires of second-stage assemblies, cold flow checks with flight harnesses, and full system power on rehearsals with physical interruptions present. Serial production plans for R16 components were recalculated to absorb the delay. Brigade training syllabi were rewritten to mirror the revised ground operations. The leadership accepted that a first deployment would move right on the calendar, and that performance reports would emphasize procedural robustness rather than the raw count of launches. The Commission also pushed for a structured method of learning from near misses. Archival searches retrieved incident reports from other families, R7 oxygen loading anomalies, cruise missile standfires, solid motor insulation defects, and extracted patterns. Where had energized checks overlapped with hazardous fluids? Where had connector designs allowed ambiguous insertion? Where had authority gradients suppressed abort calls? These patterns were distilled into cross-program advisories and appended to test documentation. The change was bureaucratic but substantive. Future deviations would be judged not only against local checklists, but against a centralized catalogue of known failure modes. By the end of this phase, the investigation had reached its most intense point of coordination. Pad fragments catalogued, witness sequences synchronized with instrument traces, bench tests replicating plausible command paths, and policy orders codifying revised safety logic. Workforce reconstruction plans with named trainees and dates were set in motion. The program, still classified, had shifted from emergency response to a quantified redesign of procedure, interlock, and training. The peak did not resolve debates over individual decisions. It converted them into engineering requirements and command rules that would govern all subsequent work on storable propellant missiles at the range and beyond. Adaptation began at the level of everyday practice. Range operations rewrote shift routines so that hazardous steps were never co-located. Fueling, electrical energization, and pyrotechnic handling were separated by time blocks with explicit clearance phrases broadcast on a dedicated net. The revised routine defined who spoke, in what order, and what words confirmed each boundary. The new protocol introduced negative confirmations, statements that a line was open, a bus was de-energized, a pin was installed, followed by a second officer repeating the status. These steps lengthened preparations but reduced ambiguity that had previously been resolved by proximity and rank. Engineering groups converted commission directives into hardware. OKB 586 issued change orders that added keyed connectors to second-stage control harnesses, eliminated shared returns where transient coupling had been possible, and inserted dedicated test sockets that could not energize firing chains. Bench tests at the plant and at the range reproduced the energized sequences, with the revised wiring to verify that no transient could excite the ignition relays when safing devices were in place. Document sets were restructured so that any temporary jumper or test plug carried a unique identifier and a usage log, preventing untracked devices from remaining in circulation. These measures turned what had been local shop practice into auditable configuration control. Training adapted with similar specificity. Survivors, shop peers, and newly appointed trainees attended short courses that reconstructed the October sequence, not as narrative, but as a series of decision points tied to instrumentation. Exercises used paper checklists with simulated alarms to practice halts and evacuations under time pressure. The strategic rocket forces integrated these drills into brigade syllabi so that procedures learned at Baikonur would appear identically in regiment manuals. In technical schools, curricula added modules on hypergolic handling, gas detection thresholds, and decontamination, with quantitative tables rather than general warnings. The aim was to make hazard recognition a skill measured by numbers and switches, not by intuition. Authority structures adjusted without removing command responsibility. The range commander retained the right to approve operations, but a designated safety officer gained the power to stop work visible to all networks. This stop authority did not lapse when a marshal or chief designer was present. Appeals were defined. A chief could request reconsideration, but the default during dispute was halt, evacuate, and reconvene. The new pattern preserved decisive leadership for schedule and scope, while relocating safety decisions to a role measured by thresholds and checklists. In interviews, officers reported that this clarity reduced the pressure to remain on the pad to demonstrate commitment. Resource management reflected the personnel losses. Plants and units mapped critical skill nodes and created substitute pools. Wiring specialists cross-trained on pneumatics. Telemetry technicians learned to operate decontamination gear. The objective was not to blur professions, but to ensure that a pad team could reconfigure when absences occurred. Documentation recorded who held primary and secondary competencies, so that rosters could be built with redundancy in mind. The closed city's education system quietly expanded enrollment in technical preparatory tracks to refill pipelines over the next 2 years. Medical and emergency services institutionalized their experience. Decontamination tents were standardized, with heated antechambers and labeled bins for contaminated garments. Fire units adopted agent tables that matched tank volumes and line diameters for storable systems. Approach routes were re-evaluated with attention to wind patterns known for the steppe in October. Hospitals established protocols for differentiating thermal injury from toxic inhalation, with stock levels for oxygen, dressings, and antidotes set by range calendars. These were not symbolic responses. They were parameterized plans connected to launch season data. The investigative method itself became a template. The grid mapping of fragments, chain of custody for logs, cross-correlation of testimony with instrument traces, and off-site replication of disputed command paths were formalized as standing orders for future incidents or near misses. Later, anomalies at unrelated stands would be documented with the same structure, allowing comparisons across programs. This normalization of evidence handling reduced later debates about memory and preserved the ability to draw engineering conclusions independent of hierarchy. Culturally, adaptation was visible in small but persistent patterns. Senior officials continued to visit pads, but observation points were relocated behind physical blast shields and outside evacuation rings. Walkdowns occurred only during unfueled states. The practice of remaining near the vehicle during energized tests diminished as the new clearance protocol made proximity irrelevant to decision speed. Commemorative practices developed inside the closed community. Internal calendars marked 24th October with schedule pauses, not for public display, but as a planning constraint. The intention was neither punitive nor celebratory. It was a recurrent reminder to run checklists by the new rules. Comparative analysis was also part of adaptation. Analysts examined open and clandestine information about foreign storable programs to benchmark interlocks, ground support designs, and crew spacing. Where data suggested that other services separated energized verification from fuel load, or used permanent hardwired interrupters between test sockets and ignition lines, those features were evaluated for domestic adoption. Reciprocal lessons flowed in the opposite direction years later, when unrelated programs experienced silo or pad incidents. Cross-program exchanges used the common vocabulary developed after October to move quickly from narrative to technical remedy. The psychological toll was addressed through procedural integration rather than rhetoric. Debriefs were conducted in groups organized by function, with an explicit purpose: to capture data and to restore teams to known routines. Personnel files noted temporary reassignment for those requesting distance from pad duties. Training slots were offered without penalty to re-enter after an interval. Commissars provided administrative support for families without public ceremonies, consistent with classification, while ensuring that dependents received transfers and benefits enumerated in regulations. The effect was to keep personal losses acknowledged inside the system that had to continue work. Innovation occurred at the margin where engineering and operations met. Range engineers introduced perimeter cameras and gas sensors, whose readings were broadcast on the same net as clearance calls, enabling the second confirming officer to rely on independent instruments rather than verbal reports from the pad. Telemetry teams added channels that recorded power bus behavior during ground tests, creating traces useful for both immediate troubleshooting and later audits. Designers proposed modularizing second-stage control units so that disputed boards could be swapped out without disassembling the entire assembly on the tower, reducing the incentive to perform on pad wiring changes. The adaptation cycle closed with measurable outputs. Revised interlock diagrams were signed, issued, and archived, New checklists with clearance phrases were printed and distributed. Training records showed initial classes completed and secondary qualifications awarded. Emergency inventories met the new tables, and pad geometry reflected expanded radii and relocated observation points. None of these changes erased the sequence that had produced the disaster, but each converted a lesson into a rule, a component, or a habit that could be audited. The program regained tempo under these constraints, establishing a mode of work in which risk was managed by explicit thresholds, standardized language, and engineered separation between diagnosis and danger. The turning point emerged when the technical, organizational, and political tracks converged on a single, testable conclusion. The configuration that combined a fueled first stage, an energized second stage, and late logic alterations could produce an unintended ignition path even with partial safing measures in place. This conclusion, reached by correlating bench replications with recovered hardware and instrument traces, reframed the inquiry from a search for culpable individuals to a focus on configuration states that would be disallowed henceforth. The directive that followed had two non-negotiable clauses. First, no energized verification of stage ignition logic could occur with propellants aboard, regardless of schedule. Second, any temporary element, jumper, plug, bypass, used during diagnosis would have an identity, a custody chain, and a removal confirmation recorded with equal weight to arming commands. With these clauses issued under government signature, authority shifted from ad hoc authorization at the pad to codified thresholds that future leaders could not waive without generating traceable violations. This decision altered the geometry of operations. Pads were recharted so that evacuation rings were physical, not only procedural. Gates closed automatically during declared energized states. Signal lamps were visible beyond the immediate site. Guard units received authority to deny entry to any rank during a red condition. The new geometry made presence less consequential than configuration. A marshal standing near a closed gate could not accelerate a step by proximity. Only the recorded clearance could advance the flow. The range commander reported a measurable effect within weeks. Fewer people in hazard zones during energized tests, reduced crosstalk on nets, and a consistent sequence of clearance calls reproducible across shifts. The change was not symbolic. It was manifest in time-stamped logs and camera records that could be audited by any later commission. Program momentum pivoted when a full-scale rehearsal validated the revised protocol. Engineers assembled a second stage with production parts from the same series as the damaged vehicle, mounted it on a ground stand with flight harnesses, and executed the power-up sequence with hard physical interruptions in place. Instrumentation recorded bus behavior, relay dwell times, and induced transients across a spectrum of temperature and humidity conditions representative of autumn at the range. The absence of spurious ignition signals under these constraints provided the necessary evidence to progress from study to controlled test. When the first post-accident flight attempt occurred, it followed a stepped approach, roll-out, unfueled electrical verification behind closed gates, defuelable cold flow checks, fueling with clearance rings enforced, and an ignition with only essential personnel located at positions defined by the new map. The outcome, stage ignition, separation, and flight according to plan, was reported in classified channels with the same tables that had framed the risk. The verification of a safe path forward, not the single success, constituted the turning point for the program. The decision framework for risk communication also changed. Internal reports ceased to describe near readiness as evidence of progress. They tabulated completion of gate conditions, training courses executed, interlock reviews signed, evacuation drills passed, alongside technical milestones. This reframing affected funding and deployment calendars. Schedules lengthened on paper, but a new metric appeared: percentage of procedures validated under the revised doctrine. Brigades preparing to receive hardware were evaluated not only by construction readiness, but by the number of personnel qualified in the clearance net, the rate of false alarms during drills, and the speed of orderly evacuation when triggered. The missile enterprise began to measure itself in process adherence as well as in flight counts. The political dimension pivoted from celebratory forecasting to guarded continuity. Leaders who had previously synchronized demonstrations with commemorations now couched internal briefings in terms of reliability and survivability. The narrative emphasized that the transition to storable propellants demanded doctrine distinct from cryogenic operations, and that this doctrine now existed in numbered orders and training manuals. Classification remained strict. Public references did not appear. Yet within the closed network of ministries and plants, the decision to privilege verified procedure over short-term display gained support because it reduced uncertainty for managers responsible for meeting force structure targets in the following years. Civilian consequences turned on administrative routines rather than public memorials. Benefits for dependents were finalized without publicity, and transfers for technical school placements were advanced to replenish skills identified as scarce. These measures had no external visibility, but they closed the loop between casualty accounting and workforce reconstitution. The turning point for families was administrative certainty. Documents in hand, assignments issued, stipends scheduled. Inside the closed city, planning calendars began to reserve 24th October as a non-operational day for hazardous work, embedded as a constraint rather than as an announced remembrance. Over time, this practice standardized across facilities, creating a consistent pause for review and training. Doctrine in adjacent programs crossed the same threshold. Solid motor stands adopted the clearance net for ignition tests. Cruise missile units instituted custody chains for temporary diagnostic plugs. Oxygen systems adopted visible gate lights synchronized to energized states. The cross-program propagation of rules marked a change from isolated lessons to a shared operating system for hazardous tests. Analysts tracked incident rates and near misses across the enterprise. The data showed a decline in events where energized checks overlapped with fluid handling. While correlation did not prove causation in a formal sense, the sequence of directives, rehearsals, and outcomes provided the practical basis for declaring the new doctrine effective. Strategically, the force planning documents adjusted with clarity. Deployment tables for storable propellant missiles shifted right by months, but the projected availability of trained crews and validated procedures stabilized, narrowing uncertainty bands in readiness reports. This stability allowed commanders to model patrol cycles, maintenance windows, and training rotations without resorting to optimistic assumptions about pad throughput. The trade was explicit: fewer attempts per month, higher probability that each attempt would meet safety and test objectives, and a reduced risk of program-wide disruption from a single incident. The investigative record reached a closure point consistent with the new posture. The final report enumerated the causal chain in technical language, listed corrective actions completed, and assigned administrative responsibility without public trials or press releases. Administrative measures included formal reprimands for procedural deviations, and commendations for those who executed recovery and reconstruction effectively. The absence of a public reckoning reflected classification, but the presence of codified corrections reflected a substantive response. The report's annexes, revised interlock diagrams, custody forms, clearance phrases, became binding references for future work. Perception among practitioners changed less by decree than by daily reinforcement. Crews learned that a red lamp at a gate would stop a general as surely as a private. Safety officers learned that their halt commands were not career risks, but defined duties. Designers learned that a late logic change would trigger a scheduled bench replication before any pad action. These conditions accumulated into a durable norm. Conversations on the net shifted from deference to rank toward adherence to checklist language. Over time, this linguistic change made the doctrine robust against turnover because the script itself, not the memory of October, carried the behavior. The turning point, therefore, was not a single meeting or a single launch. It was the institutionalization of a logic. Hazardous energy and diagnosis would be separated in time and space. Configuration would be visible and auditable. Authority to halt would be independent of rank, and success would be measured by a verified procedure as well as by flight. When the program resumed regular attempts under these rules and produced consistent outcomes, the balance tipped. A system forged in wartime habits of proximity and improvisation had adopted peacetime mechanisms of control without losing the capacity to deliver technical milestones. The catastrophe did not vanish from memory inside the system, but it ceased to govern decisions once the new doctrine proved that progress and safety could proceed together under quantifiable conditions. Withdrawal from the emergency footing proceeded in mapped stages, each tied to a threshold rather than a date. The pad remained segmented. Sectors reopened only when instruments verified temperature, gas concentration, and structural stability within order limits. Fire service units handed control to engineering teams once flare-ups dropped below specified rates per minute. Decontamination crews washed and neutralized surfaces, bagging residues with labels for later disposal. Soil removal proceeded by depth increments, recorded in cubic meters and transported to lined pits. Only after these steps did construction units begin dismantling damaged structures. The service tower was assessed member by member. Reusable elements were catalogued and irrecoverable sections cut, craned, and moved to a separate evidence yard. The control bunker and telemetry vans were checked for survivable equipment. Damaged racks were tagged and removed to workshops for component-level inspection. Casualty management entered its concluding phase as identification advanced. Remains were matched to personnel lists using unit insignia, documents, and medical records. Where identification was not possible, group designations by unit and function allowed administrative processing consistent with regulations for classified facilities. Families received official notifications through commissars and plant liaison officers, with documents describing death in line of duty without public details. Burials and commemorations took forms allowed by secrecy norms. Internal ceremonies on base or in home cities, closed rosters for attendees, and entries in personnel files tracking benefits and transfers. For some, transfer orders moved dependents to plants or schools linked to the missile enterprise, aligning support with employment pipelines. Operational drawdown at the affected complex was formalized by a stop order that required ministerial authorization to lift. Meanwhile, adjacent pads returned to work in tiers. Unfueled mechanical checks resumed first, then cold flow tests with inert fluids, then limited energizations behind closed gates. Each resumption produced a new set of logs and checklists, which the Commission treated as provisional evidence of compliance with revised doctrine. The affected pad's long-term status became a separate project, redesign, rebuilding with altered geometry, and incorporation of fire breaks and gate controls engineered according to the new evacuation radii. The schedule recognized seasonality on the step. Construction windows were planned around freeze and thaw to avoid soil instability under heavy vehicles. Programmatic consequences were immediate in paperwork and gradual in practice. Directive packages changed line items in test plans. Late logic alterations migrated to bench stands, temporary devices gained custody chains, and clearance nets became mandatory for energized steps. The R16 program recalculated its first flight date under the new constraints. Adjacent families, R7 derivatives, cruise systems, solid stand tests, adopted relevant pieces of the doctrine. Training syllabi expanded to include evacuation phrases, gas thresholds, and custody procedures. Personnel files recorded requalifications on the revised nets and tracked secondary competencies to replace losses. The closed city's schools increased intake for technical specializations linked to wiring, pneumatics, and safety instrumentation, aligning education with projected needs. Withdrawal also had a diplomatic and intelligence dimension. Externally, no public statement described the accident. Foreign services tracked indirect signals, changes in encrypted radio traffic, altered train schedules, and later imagery of reconstruction. Analysts inferred disruption to a storable propellant program, but could not fix numbers or mechanisms. Internally, classification rules limited distribution of detailed findings to named ministries and bureaus. Within that network, reports were precise. Counts of fatalities refined as identification concluded, lists of destroyed equipment by serial, schedules for stand replication of disputed logic, and tables of corrective actions with completion dates. The contrast between external opacity and internal quantification was consistent with defense secrecy practices of the period. The medical system transitioned from acute response to long-term care. Hospitals set follow-up schedules for burn recovery and inhalation injury, assigning specialists and transport allowances under garrison rules. Documentation for disability status moved through administrative channels with priority. Decontamination protocols were codified as standing annexes to medical plans for future launch seasons. Fire service inventories were replenished to the new tables, and training continued with emphasis on approach routes, wind patterns, and agent application rates appropriate for storable propellant spills. These routines formalized experience so that capability did not depend on the memory of specific individuals. Administratively, the State Commission's emergency posture converted into a supervisory role, while a separate government commission drafted the final report. Interim orders remained in force pending signature of the complete package. The final document, classified, enumerated a causal chain in technical terms, assigned administrative responsibility, and listed corrective measures completed and pending. Measures included reprimands for procedural deviations, confirmations of compliance for units that executed recovery, and formalization of the non-operational status of 24th October for hazardous work at range facilities. This date constraint appeared in planning calendars as a scheduling parameter, not as a public memorial. Workforce reconstitution progressed by quotas and dates. Plants reported numbers of newly qualified harness specialists, pneumatic technicians, and safety officers per quarter. The range reported numbers of crews certified on the clearance net and counts of drills with 0 procedural faults. The Strategic Rocket Forces revised brigade timelines for receiving equipment based on training throughput rather than pad capacity alone. These metrics shifted emphasis from hardware counts to human readiness, consistent with the Commission's doctrine that configurations and procedures determined safety outcomes as much as design. The withdrawal of emergency visibility from senior leadership matched this normalization. High-ranking visits returned to pre-accident frequency, but followed new protocols. Observation from behind shields, walk-downs only during unfueled states, and interaction with crews through the command post, rather than on platforms. Decision speed returned not through proximity, but through standardization. When an anomaly appeared, the halt phrase triggered uniformly. Evidence was collected under established forms, and resumption followed a known appeal path. Leadership attention moved to audits of adherence rather than to direct arbitration of pad actions. In the broader enterprise, the accident influenced deployment documents and resource allocation. R16-related projects rephased deliverables. Serial production absorbed revised components such as keyed connectors and isolation hardware. Depot spare inventories changed compositions to match new parts lists. Training ranges and schools requested budget lines for new instrumentation, including perimeter cameras and gas sensors tied to clearance nets. Over the subsequent year, the first successful flights under the revised regime provided data to validate the change. Ignition and separation occurred with only essential personnel within the enforced distance, and instrument logs captured the configuration states required by the Commission. The numbers closed the loop from doctrine to outcome. Information about the event remained compartmented for years. Internally, it shaped procedures across multiple missile families and test sites. Externally, the name attached informally to the incident reflected the senior official killed, and foreign accounts carried ranges for casualties that could not be reconciled publicly with classified lists. Only later, when declassification policies changed, did broader audiences access commission annexes and eyewitness statements. That later reception lay beyond the immediate aftermath. Within the time frame of withdrawal, the system's visible outputs were rebuilt structures, revised manuals, trained crews, and a calendar marked by a day withheld from hazardous operations. By the close of withdrawal, the range had transitioned from crisis to a regulated work regime in which hazardous energy and diagnosis were separated, custody was visible, and halts were authority independent. The affected complex moved from debris field to construction site to planned reopening under a different geometry. Units and plants adjusted rosters and curricula to replace skills. Families completed administrative processes consistent with closed city statutes. The missile enterprise resumed its trajectory under constraints that made future operations auditable and repeatable, aligning the lessons of October with the peacetime mechanisms needed to sustain a strategic program. Legacy unfolded along technical, institutional, and cultural lines that extended beyond a single program. In technical terms, the findings and directives generated after October 24, 1960, became a template for all Soviet work with storable propellants. Interlock logic was redesigned to enforce physical separation between diagnostic paths and ignition chains. Keyed connectors and dedicated returns reduced the chance of unintended coupling. Custody forms for temporary jumpers and plugs made improvised devices traceable. These measures did not belong only to the R-16. They migrated to follow-on families in development and to ground support equipment at ranges far from the original pad. Years later, launch documentation across unrelated programs still carried clearance phrases and two-person confirmation steps written in the same vocabulary that emerged from the Commission. Institutionally, the case altered the balance between command presence and procedural authority. During the war, officers had often gained reliability by standing close to danger and compressing decisions. At Baikonur in 1960, that habit intersected with hypergolic propellants and energized circuits. The adaptation that followed gave a safety officer negative authority that did not depend on rank. It enlarged evacuation radii and automated gate closures during energized states. It made configuration states visible through cameras and lamps broadcast on a dedicated net. These changes redistributed responsibility without diminishing accountability. Senior leaders continued to set schedules and allocate resources, but hazardous steps proceeded only when instrument thresholds and checklist steps were satisfied. Over the next decade, this distinction allowed brigades to train in a repeatable language of halts and clearances, reducing dependence on individual judgment under pressure. The event also shifted the metric by which progress was reported inside the classified enterprise. Before October 1960, lines on internal calendars tracked pad throughput and attempts per month. After the Commission, calendars included counts of validated procedures, drills completed without faults, and the percentage of crews qualified on the clearance net. This reframing allowed managers to calculate readiness with narrower uncertainty bands. Deployments moved to the right in time, but the predictability of the human system increased. For a strategic force, predictable training and maintenance cycles were as consequential as raw counts of launches or missiles. The legacy in this sense was an operational grammar that could be audited and enforced. Culturally, the range absorbed the accident into routine rather than ritual. Within closed city constraints, families received benefits and transfers. Technical schools expanded intake for skills identified as scarce. The calendar marked October 24th as a non-operational day for hazardous work. These measures were not public memorials, but they created a durable institutional memory. New personnel learned the significance of the date through schedule and syllabus, not through media. The effect was to embed recollection in the mechanism of prevention. Survivors and newcomers operated under the same phrases and thresholds, which reduced the reliance on oral accounts of the disaster to maintain caution. Comparative perspectives reinforce the broader significance. Storable propellant programs in other countries encountered their own incidents in later decades, and open literature shows convergent solutions. Physical interlocks, two-person rules, energized tests conducted away from loaded stages, and evacuation perimeters enforced by automatic barriers. The Soviet changes after October 1960 fit this pattern. The logic was transferable because it derived from properties of the technology and from the behavior of organizations under schedule pressure, rather than from uniquely Soviet conditions. Where differences remained, they reflected local doctrine and infrastructure, not a disagreement about the basic separation of diagnosis and danger. Historically, the accident illuminates how wartime habits persisted into peacetime industry and how they were reconfigured by technology. The practice of compressing time by placing authority at the point of action had delivered results on bridges, railheads, and artillery lines between 1941 and 1945. In 1960, the same reflex met a system where energy was stored in toxic liquids and electrical commands could propagate along unintended paths. The Commission did not attempt to erase the habit of personal responsibility. It constrained its expression with rules that were testable and visible. The resulting doctrine preserved decisiveness where it was still useful, allocation of effort, acceptance of revised schedules, and removed it from steps where instruments and interlocks could prevent harm more reliably than proximity could. The episode also shaped the long arc of transparency. At the time, the state maintained secrecy. Reports circulated within ministries and design bureaus. Casualty lists were held under classification, and external communications contained no acknowledgement. Decades later, when archives began to open, researchers could compare commission annexes with eyewitness accounts and hospital records. The ranges in casualty figures found in public sources reflect this layered history. Initial internal tallies compiled in the first days, formalized counts after identification, and later public reconstructions drawing on partial releases. The historiographical lesson is that numbers migrate across time with the status of documents. The Commission's approach, instrument traces, chain of custody, bench replication, provided a model that historians later used when correlating testimony with declassified technical material. Strategically, the disaster influenced the trajectory of the missile enterprise in quantifiable ways. First flights resumed under revised constraints. Serial production incorporated new connectors and isolation hardware. Brigade training syllabi matched range procedures. The evidence for this influence is visible in dated change orders, reissued manuals, and logs of drills that list participants and outcomes. In the larger balance of power, these administrative artifacts mattered because they converted a high-variance process into a lower-variance one. A force that can predict its own training throughput and safety margins can schedule patrol cycles and maintenance windows with fewer disruptions, which affects operational availability even when headline numbers do not change. For contemporary readers, the case offers a lens on how organizations learn under constraint. The Commission did not resolve every memory discrepancy or assign all causality to a single decision. It prioritized configurations that would be forbidden, procedures that would be standardized, and instruments that would make states visible. Its legacy was a sequence of enforceable rules that could be audited by people who had not been present in 1960. That transferability is the marker of institutional learning. The R16 program moved forward, later families incorporated the doctrine, and the range's geometry, gates, lights, cameras, marked perimeters, made decisions less dependent on personalities and more dependent on measurable conditions. In sum, the October 24th event demonstrates that the boundary between war-shaped command culture and peacetime industrial safety is not a line, but a set of choices. In 1960, choices made under political calendars and technical novelty produced a configuration where risk and authority converged at a pad. The choices made afterward separated energy from diagnosis, rank from halt authority, and urgency from proximity. The deaths recorded in the closed lists, the orders changing interlocks and checklists, and the silent calendar pause each year form a record of how a strategic program absorbed a disaster and translated it into procedures that governed its subsequent work.